All right. So I hope everybody saw that I posted some solutions to the diagnostic quiz from yesterday. Again, this was very helpful for me. So if you look at the syllabus, you may have seen that the first week and a half were dedicated to review. So we'll do at least that much, probably a little bit more on the review of vectors and vector algebra. Okay, so let's just get into that right away. So let's discuss dot products, angles, and orthogonal projection. Right. So geometrically, you're probably at least slightly familiar with viewing, say, for example, the real numbers as a geometric object, a line, right? So here's the schematic diagram, right? Here's R, a line. Similarly, I can look at two copies of R arranged in a perpendicular fashion. And this gives me the plane, R2. Same. If I take three axes and arrange them in a mutually perpendicular fashion. Oh, sorry, R2. I get space, right? So line, plane, and the okay, so this is purely geometric. Now, the point is that each of these objects, the elements of each of these objects, right? These are ordered pairs, right? X1, Y1, X2, Y2, X3, Y3. Here's X1, X2, X3. At some point, X1, Y1, E1. The point is the elements of each of these geometric sets are viewed as vectors. Right? So when I look at this picture, there's no structure that necessarily relates these 2 points, or these 2 points, or these 2 points. I mean, when we look at the number line, probably familiar from arithmetic that you can add things and there's a geometric interpretation of addition, right? So when I say that in general, these sets can be viewed as sets of vectors, I mean that there is in fact a way to add these. Okay. So in general, if we take V1 and V2 as elements of Rn, is this curvy little e familiar to people? No. Okay. So this is a symbol that means is an element of. So all I'm saying is I'm taking 2 vectors in n-dimensional space. Obviously, I can't draw more than 3-dimensional space, but hypothetically, I can continue to add axes in a mutually orthogonal way for arbitrarily large positive n. So in general, if I take 2 vectors, here's what I'm allowed to do. There is an operation of addition. If I take any 2 vectors in n space and add them together, I get another vector in n space. We call this closure under addition. Okay. What else can we do? For a real number C, right, just an element of R1, we necessarily must have that C times V1 is an element of Rn. Scalar multiplication, yeah. C is just a constant. It's just any element of R, right? It's just a real number. Okay, so again, let's refer back to our picture here. If I take this vector here, x1, y1, and I say multiply it by 2, what I'm doing is doubling its length. Right? This is 2 times x1, y1, which is just equal to 2x1, comma 2y1. Hence this term scalar multiplication. I'm scaling the vector, either lengthening it or shrinking it. Thirdly, I'll write this and then we'll say a few words about it. C times V1 plus V2 hat is equal to C times V1 plus C times V2. That is to say, the addition operation and scalar multiplication interact nicely together. I can distribute scalar multiplication across a vector addition. Okay. And we can also do that in the opposite order, whatever that means. Well, let me explain what that means. If I take 2 scalars, C1 and C2, and multiply them by V1, I can distribute the vector inside the scalar addition. Okay. V1 plus C2 V1. I should be explicit here for C1 and C2. Again, elements of R, this scale. Okay. Right. Write that down. An element of real numbers is called a scalar. Okay, so it so happens that any collection of yes. Yep. Yeah, this just means is an element of. Anytime you see that. So no, so this is saying when V1, V hat 1 is an element of Rn, that's saying that it's an element of this set, which is the set of n-dimensional vectors. So, exactly. Yeah. Right. So this curvy E just means is an element of whatever the set is on the right. Yeah. Is that okay with everyone? Right. So it so happens that anything that satisfies properties 1 through 4 here, any set that satisfies these properties doesn't have to be Rn. That's a vector space. Okay. So we'll only be concerned in this course with Rn or n positive digit. But just be aware that we could replace Rn with some arbitrary set where there is a notion of addition and scalar multiplication by real numbers. But for us, we're only concerned with Rn. Okay. These are the axioms for a vector space. So Rn is a vector space for all positive n. Okay. So let me take this opportunity to mention, I think that it would be really helpful if linear algebra was required to take this course, because you can get a lot more out of it or go in much greater depth if you know a little bit of linear algebra. But it's not required. This is the maximum amount of linear algebra you need to know, except for taking the determinant of certain matrices, which we'll discuss. Okay, but just as a point of interest, in the textbook, at the end of every chapter, there's additional linear algebra remarks and interpretations of the content. So if you're interested, or if you're taking linear algebra or have taken it before, I strongly encourage you to refer to the textbook at the end of every chapter, and I'm happy to answer any questions. Okay. Good. But really, all we need is a computational view of how to work with vectors. Right? So basically, we want to be comfortable with essentially everything that was on the quiz in an arbitrary situation. And that's where we're going to try to get over the course of the next week. Okay, so so in general, addition is the key operation that you can do between vectors. Scalar multiplication, also important, but conspicuously absent from this list of axioms is a way to multiply vectors. Okay? So let's see what we can say about multiplying vectors. It's not that nice. Okay, this is why vectors are a distinct type of structure than just real numbers. Except, of course, in the case where n is equal to 1. Because there is no good way to multiply arbitrary n-dimensional vectors together. But let's see what we can do. Okay? So the dot product is a kind of multiplication of vectors. It takes two n-dimensional vectors in and outputs a scalar. Okay, so right away you see that this is in a certain sense defective, right? When we talk about multiplying numbers, we multiply two numbers together and we get a number of the same type back out. The dot product is an operation that we put two n vectors in and we get a scalar out. So this is less than ideal, but we still care about it a lot because there is geometric content behind that. It tells us about the relationship between the two vectors that we put in the dot product. So let's discuss that. Right. So dot product gives us a way to determine the angle between two vectors. Okay, question. What do I mean by the angle between two vectors? Yeah. I mean, you're right in two dimensions. What if I have, say, two 5-dimensional vectors and I want to determine the angle between them? What does that mean? It's impossible to draw, but the intuition is correct. What does it mean to describe an angle between two vectors? Yeah.
Once you put it on the one plane, the both of them fly on.
Perfect. So the point is that two vectors, no matter their dimension, and as long as they're not parallel, form a plane. Right? Look at the case of 3 dimensions, something we can actually visualize. Right? If you take two non-parallel vectors in 3-dimensional space, they'll always form a plane. Okay? So when I say the angle between those two vectors, I mean the angle that spans in that plane that they form. So in a way, you're right. It's hard, you can't draw a 5-dimensional thing, but there is a 2-dimensional thing sitting inside that 5-dimensional thing where those two vectors reside. And that's what you're measuring. The angle between them in that plane. Okay. So right away, this is kind of miraculous, right? We can come up with a coherent notion of angle measurement between two things in arbitrary dimensions by this computational tool, this type of defective multiplication. Okay. So here's the definition. let's let v hat be given by components v1, v2, all the way up through vn. And w hat be given by components w1, w2, all the way up through wn, both of which are elements of Rn. Right? This is somewhat redundant. I say they're elements of Rn, but you knew that already because they both have n components. Okay? That's why you become comfortable with this notation. Okay. Then the dot product excuse me, B and W is given as B dot W. So all we do is multiply component wise and add together the results. Okay, and I want to write this compactly. We will write a bunch of sums throughout the term. So another piece of useful notation is that we'll use sigma notation, right? The sum from I equals 1 to n of v sub I times w sub I. Okay, so in some sense, this is a kind of naive thing to do, but it turns out to be a very useful definition. Okay. I'd also like to point out in other non-vector related math classes, sometimes you see a dot used for this multiplication of numbers. Here, let's just reserve this for the dot product. If I'm multiplying numbers together, just put them next to each other. Okay. To avoid confusion. Okay. So, let me tell you some nice things about this construction, some properties that this type of multiplication obeys. You don't get a vector back out, but it still has a bunch of nice things about it. Okay, so just as a setup, let's take a hat, b hat, and c hat in Rn. And let's take scalars, R and S. Then we have the following properties. A hat dot b hat is equal to b hat dot a hat. Commutativity. That's pretty nice. A hat dot b hat plus c hat is equal to a hat dot b hat plus a hat dot c hat. Again, the operations of vector addition and dot product interact nicely together. Sorry. Property number 2. Property 3. Let's suppose I scale a hat by r, which gives me another vector in Rn, and I want to take the dot product of that with b hat scaled by s. Well, then as it turns out, I can just pull all the scalars out and keep the dot product of the two vectors separate. Right, so that's equivalent to or equal to scaling. Well, let me just write this. A hat B hat times RS. What's my output here? What is this quantity? Yeah, it's a scalar, right? Because the dot product output's a scalar, and R and S are scalars. So this is just a real multiplication of real numbers, right? Whereas on the right, we have a scaling, and then a dot product, which is also a scalar. Yeah. Okay. So, four. What happens if I take the dot product of A with itself? Okay. Well, I'll tell you. Same as taking the magnitude of A and squaring it. Okay. What's the magnitude of A? Maybe something that up. Yeah. Yeah. That it's the square root of the sum of the squares of the components. Okay. Right? Okay, so let's just justify this really quick. So first, remember that the magnitude of a vector is just the square root of the sum of the squares. Yeah. Okay, so everybody knows this double-tailed arrow. I'll tell you what it means. This means implies. Okay, so just remembering the formula for the magnitude of the vector A hat implies that if we square this, we just get the sum of the squares of the components. Which, if I write out, I get A1 times A1 plus A2 times A2 plus all the way up to AN times AN. Compare this with the definition of the dot product. Right? A hat. An empty square means the end of a proof. Okay. Knowing this justification is not important. I think it's important that you see it at least once. But remembering this formula is important. Okay. Right. What else is nice about the dot product? The absolute value of the dot product of A and B hat is less than or equal to the magnitude of A times the magnitude of B. Furthermore, with equality, if and only if A and B are parallel. Okay. Oh, I'm sorry. Yeah, the camera zoomed in. Some of that was out of frame for the people on Zoom. Okay, so there's an important note here. Double bars is familiar from working with real numbers, right? This is absolute value. But here we've taken double bars of a vector. I told you that this is the magnitude of the vector, right? So we're overloading the notation of double bars. And I do this because you look at an arbitrary textbook, it will be used in both ways. Okay? It's your job at all times to check the type of object you're applying double bars to. Okay? A dot B is a scalar. So when I put double bars, I'm talking about the absolute value. A has a vector and B has a vector. So when I use double bars there, I must be talking about the magnitude of the vector. Okay, so the statement is actually a little bit more profound than it looks, because we're relating two different operations, right? Taking the magnitude and multiplying it together, and taking the absolute value of the dot product. Okay, so this is just an issue to be aware of when you're computing, when you're writing things out, and when you're reading from an arbitrary text. Okay. So yeah, let me just note this. This is called the Cauchy-Schwarz. Schwarz is a D inequality. That's just a historical note. Right? Those are the people that independently discovered it. Okay, so one more important property. Property 6. We have a formula for the dot product of A and B, which is just the magnitude of A times the magnitude of B times the cosine of theta, where theta is the angle between A and B. Right, where we just discussed what the angle between two n-dimensional vectors is, right? The angle in the plane that they span. Okay, so this is related to a question from the quiz, right? I asked you to compute the angle between two vectors in the plane, two three-dimensional vectors, but they happen to lie in the plane. That is easy to compute, the xy plane. Okay. Let me just say a word about this. So by property 5, here's one thing that you know. We have the following string of inequalities. Right? I've taken property 5 here, right? This is an absolute value. So I can unfold this inequality to be two inequalities. Right? If I drop the absolute value sign. And then divide through by the magnitude of A times the magnitude of B. And then I know that I must be bound between -1 and 1. This quantity, A dot B, divided by the magnitude of A times the magnitude of B. Right? Okay. So what this tells us it's valid to compute theta is equal to the inverse cosine of a hat dot b hat divided by the magnitude of a hat times the magnitude of b hat. Sorry. That is to say, this quantity is always in the domain of inverse cosine. Okay. If the Cauchy-Sforza inequality did not necessarily hold, then this would not always be a valid formula. But because of property 5, you can always compute the angle of between two vectors if we can compute the dot product by taking the inverse cosine of this quantity. Okay, so I would say this is a valuable formula to remember. Okay, so right. Here's a corollary. Now that we've expressed the dot product as some formula involving the angle between two vectors, we can say the following. A hat and B hat are in Rn. Then A hat and B hat are perpendicular. If and only if the dot product is equal to 0. Okay. And we can say more. Theta is acute. If and only if the dot product, which is a scalar, remember, the dot product is greater than 0 and obtuse. If and only if the dot product is less than 0. Okay, so again, this is tie this back to what we were saying at the outset. Even though the dot product is some degenerate kind of multiplication, it contains a lot of geometric information about how the vectors relate to one another. Just by sign analysis. And this is owing to the fact that these are the, first of all, the magnitude of a vector has to be positive, right? So the sign of the dot product is completely dictated by the value of the cosine, right? So that's why we can tell if A and B are acute, orthogonal, or obtuse relative to one another just by the dot product, because that dictates the sign of the cosine function. Good. Okay. So let me give you a problem, and then we'll work on it for a couple minutes, and then we'll talk about it. So consider vectors in R3. given by A is 1, 2, 3. B hat is -6, -6, 6. And C will be given by 0, 2, 1/2. So for each pair of vectors, determine if the angle between them is acute, right, or obtuse. And since we're in this format of seating, talk to me neighbors. If you want. Okay, so let's discuss. First and foremost, we're asked to determine the type of angle for each pair of vectors. How many computations am I going to have to make here? Seeing a couple threes. Why is that? Exactly, because the dot product is commutative. So, for example, A dot B is the same as C dot A. So I don't have to make 6 computations. Just 3. Okay, so why don't we just start with A dot B? What did we get here for A dot B? Yeah, 0. Okay, let's verify that really quick. A dot B. What do we get? We get 1 times -6 plus 2 times -6 plus 3 times 6. Rule of arithmetic. In fact, that's 0. Right? Okay. How about now? What? Which one should we do next? A and C. Okay. A dot C. What do we get for this? Say again. 5.5. Yeah, I think that's right. I'll just write out the multiplications. Okay. So 3 times. What do you get? Multiply each of the components and add them together, which gives you 5.5 or 11.5 if you like. Again, I think I mentioned this the other day. I don't care if how you simplify your answers, as long as it's a correct answer. Doesn't matter what format it's in. Good. So what does this imply? Yeah, that is a cube, right? Which is greater than 0, which implies cube. Okay. Last one. D dot C. What was our conclusion here? Let's say, yeah. -9. Yeah, that's what I got as well. Which is less than 0. Implies obtuse. Okay, so good. I'm glad that this came across so easily, right? There might be some question as to what form of the dot product you should use, right? Whether you should use this formula that involves the angle explicitly, and you have to compute the magnitudes, or just the definition. But the point is that you can vary. First of all, the definition is easier to compute. It takes fewer steps to actually compute. And if you run it on a computer, it takes less time to run. So if we're just asking about orthogonality or the type of angle, just the type of angle between two vectors, we should use the definition. This alternate formula comes in handy when we actually want to know the value of the angle between two vectors. Okay? So really quickly, let me ask you to find the angle between A and C. And verify that it's in fact a cube. All right, so probably at this point you realize this is not going to be a very pretty thing. Right? You need a calculator to evaluate. So maybe we should just talk about it instead. As long as you know the steps, like I don't expect you to know arbitrary cosines of an arbitrary or an inverse cosine of an arbitrary fraction between -1 and 1. Okay, so what's steps do we have to take in order to compute this? What's necessary to compute in order to compute the angle? Yeah. Yeah, we need the magnitudes of A and C. First and foremost. What's the magnitude of A? Well, it's the square root of 1 squared plus 2 squared plus 3 squared. Or in other words, square root 14. And the magnitude of C is 0 squared plus 2 squared plus 1/2 squared, which I simplified to 1/2 root 17. Yeah. Doing this by hand. Okay, good. And now we can just apply this formula that I wrote a box around before, right, for the value of theta. This implies that theta is equal to the inverse cosine of the value of the dot product. We computed that before. I'll write it as a fraction now. Divided by the magnitude of each multiplied together. And if you plug this into a calculator, this is approximately 0.777 radians, or if you like, 44.52 degrees, which is in fact acute. Good. So just kind of a sanity check thing, right? I told you this way to determine the type of angle, and now when we actually compute it, it agrees with what we asserted before. Okay? This little type of approaching a problem from two directions is all important in mathematics, right? Just to make sure that the methods that you're using for different purposes agree. Okay. Okay. Good. So, now I want to talk about orthogonal projection, which is kind of a fundamental vector operation. It takes a bit more setup, but we use it all the time. And let me just say before we get into this, after we talk about orthogonal projection, we'll return to the question of trying to come up with useful ways to multiply vectors together and possibly get another vector out. Okay. The dot product turned out to be pretty nice, but it doesn't exactly satisfy our innate urge to have some type of multiplication that is closed in vectors. So after discussing orthogonal projection, we'll discuss a different type of multiplication of vectors. But for now, let's discuss orthogonal projection. So, given a vector f and a non-zero vector b, we often want to find the part of f parallel to b. What do I mean by this? Well, let me draw you a schematic diagram. Here's my vector f. And here's some other vector, non-zero, b. What I would like to do is decompose the vector F as a sum of a vector F sub V, which is parallel to V, and F sub N, some vector which is orthogonal to V. Okay? Remember, this little box means a right angle. Okay, so right, so very often in this setup where we have a vector F and a non-zero vector V, we're interested in this part of F, which is parallel to V. Now, let me just say a word about vector addition. We know how to add vectors, right? Algebraically. If I have two-dimensional vectors, x1 comma y1 and x2 comma y2, how do I add them together? Okay, if there's no immediate answer, let me remind you. So x1 comma y1, b, x2 comma y2. Then we know that a plus b is another two-dimensional vector, right? And how we arrive at that is we just add component-wise. You can see is an element of R2, right? So that's how you add vector addition. Addition algebraic. How do we add vectors from a geometric standpoint? Yeah. Yeah, exactly. So now let's draw our scenario. So here's our vector a hat, x1 comma y1, and here's our vector b hat, x2 comma y2. Right? Again, this is just schematic. Right? I'm just choosing some arbitrary positions for these to be in, and there's no assigned values for the x and y. So how do I add these together? What I do is, okay, so this is kind of an important point. Remember that when we draw vectors, we typically draw them with their tails at the origin at 0, 0. That's standard. However, we can move them around the plane as much as we want, as long as we keep the relative angle and the magnitude the same. And that's the same vector. Right? So here's what I do to add vectors. I start with the standard representation. And then if I want to get a plus b, I'll just slide the vector b, keeping the orientation the same. I'll slide it along a until I get to the tip of a. Right? So that is to say, this vector is also b. Remember, the identity of a vector has nothing to do with where it is in the plane. It's just about the length and the angle it makes with the x-axis when it's at the origin. Okay, so this is the same vector b that I just put up here. Now to add them together, what I do is I connect the tail of A to the head of B. So this vector here is A plus B. And a good way to remember this is that vector addition is commutative, right? So if I wanted to add B hat, add A hat to B hat, do it in the opposite order, geometrically, what I'm doing is sliding the vector A along B until I get to the tip of B, right? So that would give me this. This vector is also A hat, right? So when you add two vectors, what you're doing is drawing the diagonal of the parallelogram that you can form with the two vectors A and B. Okay. So, all that being said, so in our orthogonal projection picture, when I say the part of F parallel to B, what I mean is that we're decomposing the vector F as a sum of F hat sub B hat and F hat sub A. Okay, when I say the part, I mean it's a summand that adds up to F. So we have F hat is equal to F hat sub B hat plus F hat sub N. That's exactly what we've done here, right? In this picture, F hat sub B hat and F hat sub N are already tip to tail. So when I connect the tail of the first thing to the tip of the second, I get back F. But see, I'm doing the reverse process because I started with F, and then I came up with this parallel part and drew an orthogonal vector part to get back a sum, to come up with this. Okay? This is what we call decomposing the vector F hat. Sorry, the clock's not accurate. I just have to check the time on the computer. Okay, good. So, right. Let me just say, where does this subscript B hat is somewhat apparent, right? It's because it's the part of F that's parallel to B. Where does N come from? Why did I choose that subscript? Yeah. Normal, yeah. It's because it's perpendicular or normal. Normal is just a synonym for perpendicular. Okay, so right. So any vector parallel to B hat is a scalar multiple. Okay. Why is that? Yeah. Yeah, exactly. If we have a parallel vector to B, then if we put them both in the standard representation, you put their tails at the origin, then they have to lie on the same line. The parallel vector could be bigger or smaller or point in the opposite direction, but it has to be on the same line as B is. So it has to be a scalar multiple. Okay. So any vector parallel to B must be a scalar multiple. So this parallel part of F hat has to be equal to T times B hat for some real number T. Okay, so the first thing that we'll do on Monday is derive a formula for T. Okay? Because this vector, f hat sub b hat, is something that we're going to use a lot. So we want to have a formula for this T that we can just plug in our relevant data to and be able to use it right away. Okay? So have a great weekend, and I'll see you all on Monday.